sp, sp2, sp3. Which one is this one? Struggling with hybridization? Don't worry. By the end of this video, you will learn this concept crystal clear. So in this video, I'll be explaining its definition, its importance, and how hybridization occurs. And then at the end, I'll be giving a simple trick by which you can easily recognize the hybridization instantly by looking at the molecules. So stay tuned till the end of the video so that you will not miss that simple trick. So what is hybridization? It is nothing but intermixing of atomic orbitals to give new hybrid orbitals. So the resulting hybrid orbitals will be having equivalent energy. Why do we need hybridization? So it is important for two reasons. The first one is to understand the molecular shapes. If we relied only on atomic orbitals like s, p, d or f orbitals, then we cannot explain the shape of methane molecules. As you are aware, methane is having tetrahedral shape, okay? And similarly, ethene will be having trigonal shape. So why these molecules are having these shapes, we cannot explain with the help of atomic orbitals. Based on VSC-PR theory, we can understand that electron pairs, when they come close, they repel. To maintain the stability, they always arrange themselves at particular distance. But this hybridization concept gives us orbital picture of the molecule by which we can easily understand the shapes of different molecules. For example, in case of methane, carbon is in sp3 hybridization state. So that means one s orbital intermixes with the 3 p orbitals to give 4 equivalent energy containing sp3 hybrid orbitals. So this formed hybrid orbitals will be arranged in tetrahedral shape. It is because of this reason methane is having tetrahedral shape. So we can better understand the molecular shapes with the help of hybridization concept. The other reason is the stability of bonds can also be explained with the help of hybridization. When orbitals hybridized, the newly formed hybrid orbitals make stronger bonds when compared with the unhybridized orbitals. That means the sigma bonds which are formed due to overlapping of hybrid orbitals with other orbitals are stronger when compared with the bonds that are made by unhybridized orbitals. So in short, hybridization explains why molecules have the shapes they do, and also it explains why those bonds are stronger and stable. Let us try to understand sp, sp2 and sp3 hybridization step by step. So in sp hybridization, one s orbital intermixes with one p orbitals to give two sp hybrid orbitals. So these two sp orbitals are having equivalent energy. Hence they have the ability to make two sigma bonds. So how these orbitals will be formed? So s orbital is spherical in shape and p orbitals it is dumbbell in shape. Okay, so upon hybridization it gives two sp hybrid orbitals. So this is one sp hybrid orbital and then this is another sp hybrid orbitals. Arrangement of resulting sp hybrid orbitals, if you see, they will be arranged linearly. The bond angle between these two hybrid orbitals is 180 degrees. So let us consider an example. So for sp hybridization, we can take ethane as example. So that is the first member of alkynes family. CH triple bond CH is the formula. So with respect to each carbon, now the hybridization state is sp. Let us see how it happens. So carbon atomic number is 6. So the electronic configuration is given here. So 1s2, 2s2, 2p2 is the electronic configuration. So you can count the total number of electrons. 2 plus 2 plus 2, it is 6 electrons are present in case of carbon. Now same in terms of orbitals it is written. So here only valence electrons are shown, orbitals are shown. Okay, so valence level means the second energy level. So that is 2s2 electrons and 2p2. So at second energy level, there will be 3 types of p orbitals will be there. 2px, 2py and 2pz. But here carbon will be having only 2 types of the electrons, 2px and 2py. While one of the p orbital will be empty. On excitation, one of the s electron from 2s energy level will be promoted to 2z, that is the empty orbital. So we have transferred one electron from s orbitals to p orbital. Now you can see it becomes 2s1, 2px, 2py and 2pz. So one s orbital and one p orbital, they will undergo hybridization. Okay, so they will be intermixing so that we get two equivalent energy containing sp hybrid orbitals. So this is how we get two sp hybrid orbitals, while the other two 2p orbitals will be unhybridized. They are not participating in the hybridization, so they will be left over as it is. Now first let me explain the sigma bond formation in case of ethine. So total how many sigma bonds are there? If you see here, triple bond means it consists of one sigma bond and two pi bonds. So overall here, one sigma bond and two pi bonds with respect to the triple bond. Okay. Now coming to this CH bond is another sigma bond and this CH bond is another sigma bond. So that means plus 2 sigma bonds will be there. That means overall there will be 3 sigma bonds and 2 pi bonds. Let me first explain how these 3 sigma bonds will be forming. So as I explained previously, each of the carbon is involved in now sp hybridization. That means there will be formation of 2 sp hybrid orbitals. Okay. So with respect to C1, these are the 2 sp hybrid orbitals. Okay. And similarly with respect to C2 also, that is second carbon also, there will be formation of 2 sp hybrid orbitals. So here what happens? The sp hybrid orbitals of first carbon will be overlapping with the sp hybrid orbitals orbital of the second carbon. So because of this sp-sp overlapping, there will be formation of sigma bond. Okay. So out of triple bond, one bond is sigma bond now. So that is how that sigma bond will be formed due to the overlapping of sp hybrid orbitals of the neighboring carbon atoms. Okay, now coming to the other sigma bonds, if you see, these carbons are making other 2 sigma bonds with the hydrogen. So you can see here, only one of the sp hybrid orbital is involved in the bond formation with the neighboring carbon. Okay, while the other sp orbital, in case of carbon 1 and carbon 2, they are empty. Okay, now what happens? Hydrogen, the atomic number is 1, that means it will be having one s orbital. Okay, so the other leftover sp hybrid orbital of each carbon will be forming sigma bond with the s orbital of hydrogen. So this is the s orbital of hydrogen. Okay, so this is s orbital of hydrogen will be overlapping with the sp hybrid orbital of first carbon. So this is how another sigma bond will be formed. And similarly on the other side also, the second carbon is also having one sp hybrid orbital. So with this, the s orbital of another hydrogen. Okay, another hydrogen will be forming another sigma bond. So this is how, due to s and sp orbitals overlapping, there will be formation of 2 sigma bonds. Okay, so overall due to sp-sp overlapping, there will be formation of 1 sigma bond, and other 2 sigma bonds are due to overlapping of s orbital and sp orbitals on either side. So overall there are 3 sigma bonds will be there in the structure of ethane. So as I mentioned earlier, each of the carbon will be having 2 unhybridized p orbitals left over. Okay, so let me draw those p orbitals. So these are the 2 p orbitals with respect to first carbon, and these are the 2 p orbitals with respect to the second carbon. Now what happens? These 2 p orbitals of the first carbon will be overlapping with the p orbitals of the neighboring carbon, that is with the second carbon. So that is how there will be formation of 2 pi bonds. Okay, because 2 p orbitals of the neighboring carbons are involved in this overlapping. So thus it results in the formation of 2 pi bonds. Okay, so this is one pi bond and this is the other pi bond. So that is how there will be formation of 2 pi bonds in the structure of ethane. So this is how 2 carbons present in ethane are in sp hybridization state. Coming to the bond angle, here the bond angle is 180 degrees and these 2 hybrid orbitals will be formed linearly. Obviously, the other 2 hydrogens, when they are overlapping, they will also overlap linearly. So as a result of which the overall molecular shape, it becomes linear. Coming to sp2 hybridization, here one s orbital will be intermixing with 2 p orbitals. Thus, it results in the formation of 3 sp2 hybrid orbitals. So the simple formula here, 1 plus 2 giving rise to 3. So this is how there will be formation of 3 sp2 hybrid orbitals. So all these 3 sp2 newly formed hybrid orbitals will be having equivalent energy. The example for sp2 hybridization is ethene. Formula CH2 double bond CH2. In this molecule also, each carbon will be in sp2 hybridization state. Now let us see how it is going to happen. So again I have written the electronic configuration. Carbon atomic number 6, electronic configuration is 1s2, 2s2, 2p2. So this is how the electrons arrangement will be there in the valence energy level. So these are the 2 s electrons and 2 p electrons. Now on excitation, one of the s electron will be promoted to p energy level. So that is, there will be only one electron in 2s orbital and there will be 3 electrons in 2p orbitals. Now in the next stage, one s orbital intermixes with 2p orbitals. Okay, so 1 plus 2, 3. So that is how here we get 3 equivalent energy containing sp² hybrid orbitals. So these 3 hybrid orbitals are formed because of sp² hybridization. Okay, now you can see here there will be one 2pz orbital left over which is unhybridized. That means that is not participating in the hybridization process. Okay, now we'll see how these 3 sp² hybrid orbitals will be arranged. So if you consider this as the carbon nucleus, there will be formation of 3 sp² hybrid orbitals, and the formed 3 sp² hybrid orbitals will be arranged as if they are pointing towards the corners of a triangle. So because of that reason, usually the shape of sp² hybrid orbitals will be trigonal in shape, and the bond angle between the hybrid orbitals, if you see, it is 120 degrees. So this is the structure of ethene. So if you look at this structure, you can see between carbon and carbon, one sigma bond is there. And with carbons and hydrogen, there are 4 sigma bonds are there. 1, 2, 3, 4. So overall, if you see 1 plus 4, 5 sigma bonds will be there in the structure of ethene. And between both the carbon atoms, there is one more pi bond is present, because it is double bond means one sigma bond, the other one will be pi bond. So there will be one pi bond. So overall in the structure of ethene, there will be total of 5 sigma bonds and one pi bond will be present. Now let us see how these 6 bonds are going to form. So here I have shown 2 carbon atoms. So with respect to each carbon atom, the hybridization is sp² hybridization. So you can see here 1, 2, 3 sp² hybrid orbitals are arranged across first carbon atom. Similarly, the arrangement of 3 sp² hybrid orbitals across second carbon atom are also shown. So here you can see the sp² hybrid orbital of each carbon are involved in the overlapping. Okay, so this is how there will be formation of one sigma bond between both the carbon atoms. So now you can see in the structure of ethene, 2 hydrogens are there. Okay, so these sp² hybrid orbitals of each carbon will be now involved in overlapping with the hydrogens. S orbital of the hydrogen, orbital of one of the hydrogen, and this is the s orbital of another hydrogen. So this is how, because of the overlapping of sp² and sp² of carbon and s orbital of hydrogen, there will be formation of sigma bonds. So that is how there will be formation of 4 sigma bonds. Okay, so there are 4 CH bonds are there, which are sigma bonds. Okay, and there is one carbon-carbon bond is there, that is also sigma bond. So all these 5 are the sigma bonds. So there are totally 5 sigma bonds are present in the structure of ethene. Now coming to the pi bond, there is one pi bond is present. So this is pi bond, okay, in the structure of ethene. So as I mentioned, now each carbon will be left over with one unhybridized p orbital. Okay, so let us show that with respect to each carbon. So this carbon, so carbon 1 will be having 2pz, and carbon 2 is also having one 2pz orbital. Now these 2 orbitals will be overlapping. Due to this side-by overlapping of 2p orbitals of the neighboring carbons, there will be formation of pi. So this is how this pi bond formation occurs in the structure of ethene. Now coming to sp³ hybridization, here one s orbital will be intermixing with 3 p orbitals, and that is how we will be getting 3 sp³ hybrid orbitals which are having equivalent energy. Now let us consider an example for sp³ hybridization. The example is methane. The formula is CH4. So here also carbon is in sp³ hybridization state. Now let us see how that occurs. So carbon atomic number is 6. So here electronic configuration is written. It is 1s2, 2s2 and 2p2. So when you promote one electron, now the electronic configuration becomes 2s1 and 2p3. So here in case of methane, what happens is one s orbital will be undergoing hybridization with 3 p orbitals. So all these 4 orbitals will be undergoing hybridization, and as a result of which we get 4 sp³ hybrid orbitals from s orbital to p orbital. This is how sp³ hybridization occurs. So the newly formed sp³ hybrid orbitals will be arranged as if they are pointing the corners of the tetrahedron. So that is the reason the shape of the molecule in which sp³ hybridization involved becomes tetrahedral shape, and the bond angle is 109.5 degrees. Now in case of methane, how those 4 CH sigma bonds will be formed, if you see, carbon will be having 4 sp³ hybrid orbitals. Now with each of these hybrid orbitals, hydrogens will be the s orbitals of the hydrogen will be overlapping. Okay, so this is the one s orbital of one of the hydrogen. This is the s orbital of another hydrogen. Like this, the s orbitals of 4 hydrogens will be overlapping. And that is how there will be formation of 4 sigma bonds in the structure of methane. Okay, so all these are sigma bonds. So this is how, due to sp³ hybridization, there will be formation of 4 equivalent energy containing CH bonds in the structure of methane, where the bond angle is 109.5 degrees. Now that you have understood hybridization concept, let me give you a quick tip by which you can easily recognize the hybridization state instantly, because I promised at the beginning of the video, no? So let me give you. So as soon as the molecule is given, just you need to see how many sigma bonds are present in the given molecule. That means with respect to each central atom, how many sigma bonds are present. Okay, for example, if 2 sigma bonds are present, then the hybridization involved is sp, because in sp hybridization there will be formation of only hybrid orbitals. So these newly formed hybrid orbitals can make only 2 sigma bonds. That means if 2 sigma bonds are present, means the hybridization state is sp. Okay, similarly if 3 sigma bonds are present in the molecule, that means 3 sigma bonds will be formed because of the formation of 3 hybrid orbitals. Okay, and the formation of 3 hybrid orbitals is possible in case of sp². So that is how you can recognize it as sp². Now coming to 4 single bonds, if any molecule, if any carbon atom in a molecule is forming 4 single bonds, means those 4 single bonds will be formed from 4 hybrid orbitals, which is possible only in case of sp³ hybridization state. Okay, so this is how, by looking at the number of single bonds involved for each carbon, you can recognize the hybridization state instantly. Now test yourself. Tell me the hybridization state of these molecules in the comments below. If this video made hybridization easy for you, then share it to your friends and don't forget to hit subscribe so you never miss my next chemistry hacks and concepts. Thanks for watching and stay tuned to my next videos.